All right. So we talked about the fact that if something is rolling down a ramp, you're converting gravitational potential energy to both kinetic energy and rotational kinetic energy, right? And the idea is gravity is pulling the thing down, but friction works against it and is sort of a resistive force, right? So if you imagine just taking a yo-yo from rest and dropping it, I'm not going to do it because it's going to feel unspool, but if this was a yo-yo and you imagine dropping it, there are two forces, right? Gravity is pulling it down, and the tension is a resistive force for slowing down how fast it's going, right? So in a sense, you can kind of think of this as a thing rolling down an inclined plane. The only difference is sort of the surface that it's rolling on isn't the outermost edge, it's this inner edge. Does that make sense? So there are two radii to consider. Okay, there's this outer radius and this inner radius. Cool? You see what I'm saying? Yes, heck yeah. You're right, because of the thickness of the string, you're totally right. But I think we're not supposed to worry about that.
It's massless.
Massless, diameterless string, yeah.
Unstructured also.
Right. Okay. So here's the equation that's in the book. So it says that, if you've got a yo-yo or this spool or whatever unwinding, what you do is you take the acceleration of gravity, g, and then you divide it by this mess. Here, I, COM, is the rotational inertia about the center of mass of the yo-yo. And what I've seen the book doing is they sort of ignore, and this is not a great example of it, because this isn't a true yo-yo, but like a real yo-yo, the side pieces are big, and the little spool part in the middle is very small, right? So they just kind of think of the rotational inertia of the big side parts, and they treat this as having negligible inertia. Does that make sense? Yeah. Can you guys, like if it was a real yo-yo, this middle part would be very small, right? Okay. So this basically boils down to finding, doing 1/2 mr squared, where this is the radius of the whole yo-yo. You know what I mean? Okay? And then you can see from the drawing here, I guess I should use the same notation. So that would be r squared, right? And then you can see it's divided then by mRO squared. So RO is sort of the radius of the smaller spoolie part. Cool? All right, so anyway, so that's the equation that's in the book, and it works. And hooray, cool, great. Well, where does it come from? But I don't think it makes a ton of sense to spend time deriving it, just because, again, it's one of those arbitrary equations. So let's see if we can solve the problem without that equation. So here we go. So there's a problem very similar to this in your homework. The book basically gives two yo-yo problems. So I picked one to do as homework and one to do in the notes. They're very similar. All right. This one's kind of cool. I don't know if this is true. If I'd been smart, I would have looked to see if there's a YouTube video of this. But according to the book, in 1980, over the San Francisco Bay, a large yo-yo was released from a crane. The 116 kilogram yo-yo, it's like 300 pounds just about, consisted of two uniform discs with a radius of 0.32 centimeters. So, which is actually not as big as I would think, given that. So it was... Oh, 32 centimeters, yeah, sorry. So that's the radius. So here's the diameter of this giant yo-yo. Okay? And then it's connected by an axle with the smaller radius. And so we're going to find the acceleration of the yo-yo. Cool? All right, so here is the deal. So as the yo-yo falls, make ourselves a drawing. I'm going to exaggerate the radius of the middle spool just for drawing purposes, okay? So we'll be able to kind of see what's going on here. All right, so there are two radii. There's what the drawing on the front calls RO, that's our 0.032 meters. And then there's big R, which is 0.32 meters. Cool? Everybody okay with my crappy drawing? Okay, so there are two forces acting on the yo-yo. What do you got?
Gravity.
Gravity's pulling it down. So if I want to draw gravity on this thing, where on the yo-yo should I draw that force coming from? from the center of mass, right? So here's my mass. That my force of gravity is going to be 116 kilograms times g, right? That's g for gravity, but acceleration of gravity, not g for grams. Okay? And then there's one other force. What's the other force? The tension, right? The rope is pulling up on the end of the yo-yo. Follow? So just like we did yesterday, we're going to write two equations. One equation for the net force on the yo-yo, because that'll determine the linear acceleration. And we're going to write a torque equation that'll determine the angular acceleration. Okay? And based on those two equations, we've got two unknowns and two equations. Our two unknowns being the tension force and the acceleration. Follow? So this is almost the exact same thing I did yesterday, right? Okay. So let's do our net force equation. So net force. Here's what I know. I know that my net force is going to be 116 g minus my tension, and that should equal the mass times the acceleration. Right? Total of my forces is net force. Mass times acceleration is net force. Good? Any problems? Okay, so the next thing I want to do is come up with a torque equation. So net torque. All right, well, I need to pick a pivot point. There's a good choice and a bad choice here. Thoughts, you guys? I guess it doesn't really matter, but actually, I guess that didn't occur to me, I guess. I don't know. I was thinking of choosing this as the pivot point, just because we can easily calculate the rotational inertia of that, right? Because if these are disks, then rotational inertia would just be 1/2 mr squared. I guess you could choose this to be your pivot point and then use parallel axis theorem to find your rotational inertia. I don't know what that would turn out to do. Well, I know what it would turn out to do, but I've never done it for this problem. Okay, so anyway, so here we go. So what I know is I times alpha equals, what's providing the torque? Put a C on here. What's providing the torque, you guys? The tension, right? Gravity's not going to cause any rotation, but this tension upwards is going to cause it to spin this way, right? So Ft times, what radius should I use? R or R naught? R naught, right? Because it's only this distance away from the pivot point. Follow? Everybody good? All right, and so we either need to solve for A and plug that in here, or solve for tension and plug that in here. I think I'm going to solve for tension so we can find the acceleration. So here we go. Let's see, this means that our tension force is I, about the center of mass, times alpha over R naught. So that's 1/2 m capital R squared alpha over R naught. All right, the problem is we don't want alpha. What do we want? A, right? So here's where you got to be careful, you guys. So A is alpha over something. And it's R or it's R naught. We got to figure out which one. Thoughts about which R to use? Yeah. Yeah, can you? Say that again? You might be right. I'm just not sure if I followed your logic. Say it one more time for me.
Well, the torque force is not using that as the same radius, so how is it acceleration? With the outside distance.
Yeah, so the way that we want to think about it is this. This A here is actually the acceleration of the center of mass, right? Okay? So, well, Mickey, question or answer? Your answer's right. I'm not sure if your reason jives. Say it again? Yeah, totally. Sorry, I was thinking alpha is A over R, because I was thinking about the substitution way to do. Thank you. Damn it. There we go. So I wanted alpha equals A over R is what I was trying to write. Okay, and it does turn out to be R naught, but I want to make sure we understand why. Alex, same correction? Okay, cool. Thank you guys for keeping me honest. All right, so we got to figure out why this is R naught. So here's why. When an object is rolling, do you guys understand that the velocity of a point on the outside of the surface is the same as the velocity of the center of mass? Okay. Well, remember, what we thought about was we were thinking about this thing as rolling, but what's the radius that it's rolling about? It's that inner radius, right? Does that make sense? Okay, so that's why you have to use the R naught. Okay. The outer edges are actually going to spin faster, right? Because they're at a higher radius. Make sense? Okay, cool. So these are not. All right, so this becomes, I'm going to move the 2 down to the bottom. So you get m r squared. This alpha is A over RO. So this is A over RO squared. And then the 2 is down there on the bottom, right? Good or no? So there's our tension. Everybody good? I don't know if it would have been easier for us to put numbers in before this point. It certainly could if this n is the 116. So all I'm going to do now is I'm going to take this mess. This is my tension. I'm going to plug it into that blue equation up there. Okay? So we are almost done, believe it or not. So, all right, so I'm going to rewrite that blue equation. So I get 116G minus tension. So let's see, that tension, well, M is 116 times R squared times A over 2 times R naught squared equals 116A. I'm nervous because I have not been consulting my notes. Am I getting any mistakes here? They're watching me. Okay, are we good? Okay. Hey, I don't know if this helps any. There's certainly no reason why we couldn't have just figured out this I outright. You know, just come up with a number. It turns out to be 5.93 or 5.94, I guess. I don't know if that makes it any easier. All right, so anyway, we're trying to solve this mess for A. So anybody notice anything? The masses all cancel, so that's nice. Which incidentally, well, yeah, I'm going to come back to this equation here because it's going to help us answer one of the questions later on. Okay, so it looks like I want to move all my things with A to one side. So it looks like I get G equals 1 plus R squared over 2R naught squared all times A, right? By adding this to the other side. Cool. And then divide, and you're there, right? So, let's see what we get. I didn't make a mistake here because this isn't the way I did it in my notes. So I'm just taking this and dividing it by this whole parenthesis mess over here. So 9.8 divided by, in parentheses, 1 plus R is 0.32 squared, and then divided by 2 and divided by 0.032 squared. Fingers crossed. Average. 0.192 meters per second squared. I don't know that I did that the most efficient way that I could have, but here's the big thing that I want you guys to get out of it. We wrote 2 equations, one for net force, one for net torque. two unknowns, solve for one of them. Cool? Mickey?
Is that going to be a common thing after writing that course and system equations network?
Yeah. Yeah, it does come up more often than I would like, because they're kind of a drag because of the eye. It's always kind of a pain in the neck. But yeah, they do come up. Good, you guys, or no? Okay, cool. So once you get to here, then finding your tension is pretty easy, right? Because you can just, plug in here and find your tension. And cool. That's kind of at the heart of this problem. So let's see. So we can find the tension. Incidentally, this will be the acceleration, whether the yo is going down or going up. That's what you're going to ask.
No,
Yeah. Oh, okay. All right. What else do we need to talk about regarding the yo-yo? Say that again. It's the exact same. It's literally the exact same thing. It's the same thing like when you throw a ball up in the air. Even though it's moving up, the only force on it is gravity pulling it down, right? So what happens is when it gets to the bottom, the rope starts winding around it again, and the tension pulls it back up.
Oh. That was
Cool. Yeah, right. So that's that. So I guess let me just do this. I don't know that there's a ton of sense in spending. I think we've done the hard part of this. So question C wants to know what the tension is. If you calculate it, it turns out to be 1,114 newtons, basically, with a complete disregard for significant digits. D, no, that's way less than the tension limit. And then the last part says, what if you scaled it up? All right, and it turns out that scaling it up, like if you keep everything proportional but embiggen everything, notice the mass doesn't matter, right? But if you keep everything scaled, notice if you double your little radius, you're going to double your big radius too, right? So you still end up getting the same acceleration. Okay. So interesting fact. And then obviously the tension will get bigger, right? Just because it's a heavier yo-yo. Cool. All right. Yeah, it helps.
So I have to say that any yo-yo with like that proportion is always integrated acceleration.
Yes. Cool. Okie dokie. All right, so that is that. Out at 86. The next example here in the notes. This one is actually not that bad. So it says a body with a radius of r and a mass of m is rolling smoothly with a speed v on a horizontal surface. It then rolls up a hill to a maximum height h, and it tells you what h is, all in letters. All right, and then it wants to know the rotational inertia. About the rotational axis to the center of mass, and then it wants you to say what the object might be. All right. So let's make a quick drawing, and then I want you guys to see if you can help me figure out how we're going to solve this. All right. So we've got this thing rolling with some velocity, which it looks like it's v, right? Okay. And then it's going to roll up until it gets to this point, and at this point, the velocity is 0, and the height is this mess. 3v squared over 4g. Okay, and so the question wants to know what's the rotational inertia of the shape. What's I for the shape? So, thoughts about how to start this thing? Figure out the rotational kinetic energy at what point? At the bottom. Okay. Is that the only kind of energy it's going to have at the bottom? Okay. No, I wasn't. That wasn't a loaded question. I was just asking what other kind of energy is it going to have, you guys? Translational kinetic energy, right? Okay. All right. So you're saying find the rotational kinetic energy at the bottom. Let's see if we can make something with that. So RKE is, sorry, get back into the right notation. Sorry. kinetic energy rotational is 1/2 I times omega squared. I agree with that. How am I going to find that, Patrick? Okay. Yeah, I mean, I guess we could try.
Couldn't you take, because like, wouldn't it turn into potential, gravitational potential energy?
Oh wait, say that again. You're saying that
gravitational potential energy at the top. So
There you
we
go.
find out what that is, and then it's equal to the rotational kinetic energy plus the kinetic energy of transmission.
Yeah. All right, cool. So I'm starting to hear some buzzing about energy. Yeah. So what you want to do, you guys, is you want to think about what's going to happen to the energy. All right? So the idea is, yeah, the ball's going to start out with some rotational kinetic energy and some translational kinetic energy. As it goes up the hill, it's going to lose those two forms of energy, and it's going to turn into what kind of energy, guys? Gravitational potential, right? Does that make sense? So the idea is our mechanical energy down here at the bottom ought to equal our mechanical energy up here at the top. All right, so let's see if we can maybe make something out of that. I'm just apprehensive about this because this doesn't use any of the variables that I've got. You know what I mean?
Your starting velocity, take omega out.
And you replace it with V over R. Yeah, I don't know. I don't know, monkey with it. That might work. I'm not saying that it won't work. I'm just concerned because we're not taking into account the kinetic energy yet, you know?
Sure. So I have a question. Would the ramp be frictionless or with friction? Because then that would dictate whether or not we lose.
That is a really good question. Oh, it says it's rolling smoothly. So anytime you see that, this is a really good question, you guys. She asked if the ramp had friction or not. When the book uses the term rolling smoothly, you're assuming that there's friction, and so there's no slippage. Right? That's what rolling smoothly means. I don't know that I ever explicitly defined that. So, really good point. All right. What do you mean? Yeah, or it would have to say something about it sliding. I don't know if there's a technical name for it. All right, so let's see if we can do something with this. So we know that the mechanical energy at the bottom has got to equal the mechanical energy at the top, right? Everybody agree with that? So that means that my kinetic energy at the bottom, I'm sorry, gotta start using the same notation in my honors class maybe in here, or vice versa. So I know that the translational kinetic energy at the bottom plus the rotational kinetic energy at the bottom is equal to the gravitational potential energy at the top, right? Everybody agree with that? Okay. Well, so translational kinetic energy uses velocity. So let's see. So that's 1/2 mass times the velocity at the bottom squared, right? Plus, what should I do with this rotational kinetic energy? I showed you guys something we can do with that. Anybody remember? You remember, Alex? Good. It's beta times the kinetic energy, where beta is, yeah, remember, I is beta times mr squared. So this rotational kinetic energy is this beta times this. So beta times 1/2 mv squared. Good? So that's the left side of the equation, equals all right, equals our gravitational potential energy should be mass times acceleration of gravity times height. Does that make sense or no? What's wrong? Oh, sorry, I used a G. Sorry. Sorry, that's a G. Sorry, different notation, different classes. I gotta fix that next year. Okay, are we good? Any problems, you guys? Okay, so let's see what happens. The G's cancel. What else cancels? All the V squareds and the M's too, don't they? Every term has an M in it, and every term has a V squared in it. Aha. So I've got 1/2 plus beta equals 3/4. Right? Oh, 1/2 beta, thank you. I knew something that was wrong. Good? So let's see, subtract, so you get 1/2 times beta equals 1/4. So what's beta, guys? 1/2. Cool. So what might the shape be? Solid, not solid sphere, solid cylinder or solid disc, right? That's the one that has the 1/2 on it. Okay. So, but here's the deal, you guys. Here's the important part. This is a super common problem-solving strategy, where you write an expression for the total mechanical energy at one point, write an expression for the total mechanical energy at another point, and set them equal to each other. Okay? That is like a conservation of energy, like, that's in your wheelhouse, you know what I mean? Like, you have to know how to do that. Okay? Make sense or no? Okay, cool. All right, and then I think the last example that I've done is it's just another one of these where you write two expressions, one for net force, one for net torque, and you set them equal to each other. So I think it's kind of more of the same. And I don't know that doing adds anything that we haven't already covered. So, questions, you guys? Okay. So, I told you guys that the 10.1 to 10.3 homework had to be due one day this week. So either tomorrow or Friday, and then the other day we need to learn about angular momentum. And that lecture's real short. It's like, I think there's maybe 2 definitions and an example. There's not a whole lot to it. So I guess the question is, do you want to make this due Friday and do the notes tomorrow, or vice versa? There was some concerns. How many of you are going to be gone on Friday for the DECA trip? A bunch of you. Okay. So I think it probably makes more sense to do the notes on Friday, or to do the notes tomorrow, right? So that you're not missing new material if you're gone. So let's do notes tomorrow, and then we'll make this due Friday. So I'll make Friday a Q&A day. Is that amenable to everybody? Okay, so then just so that you know, then the last couple things we've got, so next week we need to do the last chunk of notes for chapter 11, which is, all right, I'm like way ahead on, which is conservation of angular momentum. So we'll talk about precession, which is the spinning wheel thing, gyroscopes and stuff. And then we need to do equilibrium, just stuff not spinning, which I don't know why it's at the end in this book, but it is. So the goal is to get through all of that next week. If I'm being honest with myself, the odds of getting through it by next Friday are probably pretty slim. Okay, particularly since I think I might be out on Wednesday. So I think the odds of us getting through everything by Friday are slim. Okay. So I'll give you a definite answer on that probably early next week. But just kind of keep that in the back of your mind that you might have to push this chunk back a little bit. But I think we'll still be okay because the last 2 chapters we need to do, chapter 13 is gravitation, which is, it's so tedious. I'm working through it right now and it sucks. But I don't think that we need to cover it in that much detail. I think if we just did the basics on gravitation, we'll be fine. And the very last chapter we need to do is simple harmonic motion, which I think should not be horrible either, I think. So I think we'll still be okay in terms of getting through everything and having a little time to practice before the AP test. Cool? All right, pretty good? All right, we've got 12 minutes you can use to ask me questions or get started on homework, or Put her on your notes. Do what you gotta do. I'm gonna stop recording now. Kristen, thank you for reminding me to record it. I hope that my